What is up, everyone? It is Mr. Holtz, and today we are going to be talking about electron configurations. Okay, so far in class, we've talked a lot about the Bohr model of the atom, right? Where we have the nucleus in the center and concentric rings of electrons moving further and further out of the away from the nucleus as we move further down the periodic table, and we get a bigger and bigger atom, right? As the radius grows. So what we're going to learn about today is a more complicated and accurate description of being able to describe where we actually find electrons in the atom. So we're going to go over some concepts that have to do with quantum mechanics and experimental observations. However, we're not really going to get into any of the math behind it. Just know that there are a lot of complicated equations that you guys probably aren't ever going to have to deal with unless you take a quantum mechanics class. However, it is super interesting. All right, so let's dive into it. Okay, so just like I was talking about, this is the Bohr model of the atom, and we've gone over this a lot in class, right? It shows that the first ring of electrons around the nucleus of an atom has 2 electrons, and then the ring outside of that can hold 8 electrons, and the ring outside of that can hold 8 electrons, etc., based on how many elements are in that row on the periodic table, right? So basically, the way that we looked at it was, okay, well, if we have some atom, let's say it has 2 electrons in the first energy level, okay? And there's a spot for one right here. There's a spot for the second one right here, okay? So I'm just going to be filling in these blue boxes based on where we've shown that electrons appear or exist or show up in the atom based on this structure, okay? Now, if we had some amount of electrons in the second ring, if we had some atom like, let's say, boron or carbon or nitrogen, right? Something in the second row on the periodic table. Let's just say we have oxygen here. Okay, so we have 6 more electrons. If we have 6 more electrons in this energy level for oxygen, 2, 3, 4, 5, and 6. Okay, so in these boxes is where we would show that these electrons are existing. Okay, however, this is a pretty simplistic explanation of where electrons exist. However, it does support a lot of the experimental data that we find when we're dealing with atoms, right? And when we are studying their characteristics that have to do with their ability to meet or not meet the octet rule. So the valence electrons and its organization, the organization of those valence electrons around the atom kind of determine a lot of how they interact with other atoms. However, this doesn't really explain all of the experimental observations and the answers that we get when we do quantum mechanical calculations. Okay, it gives us an imperfect representation of where we actually find electrons in the atom. So what we're going to do today is we're going to start talking about electron configurations and figure out what does that actually mean, and how can we, in a slightly more straightforward way, explain where is each electron located, or which position or which spot is it occupying within a given atom. Okay, now this is going to be pretty simple. There's a lot of complicated information behind it because, again, all of this is based on quantum mechanics. However, once we start tackling some practice problems, hopefully you'll find that since most of the time we're really only dealing with writing what the electron configuration is for any given atom in the ground state, that it's pretty obvious that we're just going to be filling in one spot and then the next until we figure out how many total electrons do we have and have we found a spot for all of them. Okay, so that'll make more sense as we move on. So our explanation behind electron configurations is what I have here in blue, okay? Electrons fill spots, which we're going to call subshells, within each energy level. And by energy level, I really just mean the different levels on the periodic table as we go down from energy level 1 to energy level 7. Okay, and we'll take a look at some examples of this. Electron configurations help us understand what spaces electrons fill in the ground state and what spaces are available if the atom is energized. Okay, so we've talked about what happens when atoms absorb energy and what those electrons can do in terms of jumping up and down different energy levels, depending on how much energy is absorbed and how much energy is being released. So let's take a look at what we mean by subshells and energy levels on the periodic table. Okay, so here are some pictures that we've looked at briefly in class, but these are the actual mathematical representations of the answers that we get when we solve quantum mechanical calculations or things like the Schrodinger equation to find where electrons are going to be for specific kinds of atoms. And the specific kinds of atoms that we're talking about are dependent on where we find that atom in the periodic table. Okay, so if we look at this periodic table here, you guys will see four main colors. Okay, one color is purple, which blocks off everything on the far left side, and helium, which is far off on the right, but we kind of just think of that as filling in this spot right here. Okay, after the purple boxes, which we call the S block, and we'll get to that in a minute, we have the yellow or the green boxes, excuse me. So the green boxes over here represent what we call the P block. And again, these numbers just represent these energy levels. So we'll come back to that. In the center, highlighting all of our transition metals in this red section right here is what we call the D block. Okay, and then finally down below with our rare earth metals, all of our lanthanides and actinides, we have the F block. Okay, so in front of these letters, we have different numbers, and these numbers just represent which energy level we're dealing with. So for example, in the S block, right, everything on the left side, so this is referring to these specific elements or the electrons that are in these elements, we start at the first energy level, okay? So obviously, energy level 1 is row number 1 or period number 1 in the periodic table. And if we're talking about elements in this block right here or electrons in this block right here, we're talking about the 1 energy level in the S block, okay? Now, if we go past that, the next would be the second energy level in the S block, okay? Then after that, again, just like we're reading the periodic table in terms of going from 1 atomic number up and up and up, after 2s, we skip all the way over because there's nothing in the middle right here until we get down a little bit further. But next up is 2p. So we're still in the second energy level, okay, because we're still in the second row on the periodic table. But now we're in the p block, okay? So these are going to be p block electrons or p block atoms when we're looking at these. And we'll take a look at some examples in a little bit. So in terms of writing out the actual electron configurations, we basically just start at the beginning and count up how many electrons any given atom has that we're dealing with. And then we find spots to fill them in based on the corresponding energy levels between these different energy levels and blocks that we're talking about here. So let's take a look at where these electrons can actually go once we start figuring out how to write down electron configurations and represent where electrons actually are or which spaces or spots they're filling up. Okay, so when we're looking at these subshells within the different blocks on the periodic table, one thing we need to know is that each subshell can hold a total of 2 electrons, and we'll understand why this is the case later on. But just so you all know, the S block has 1 subshell, okay, and this will make more sense when we talk about how to format writing down what this looks like. So the S block has 1 subshell, so it can hold a total of 2 electrons, right? Because of 2 electrons within each subshell. The P block can hold 3 subshells, or has 3 subshells, so it can hold a total of 6 electrons. The D block elements have 5 subshells and can hold a total of 10 electrons. The F block has 7 subshells and can hold a total of 14 electrons. So let's look at the periodic table and see where we actually get these numbers from, okay? So we're referring to a specific subshell on a given energy level within a specific block, okay? So let's take a look at the S block. Notice how the S block covers the first column and the second column. So since every time we get a new element or every time we move over in terms of the atomic number of an element, we gain some number of neutrons, which is not really what we're concerned about right now. We gain 1 proton, which is how we increase by the atomic number by 1. And when we increase the atomic number by 1, we have to balance out that proton by adding an extra electron, right? Or if we don't have that extra electron, our atom won't be stabilized. It'll be charged because we won't have the equal number of protons and electrons. So one other thing I wanted to mention is that the reason we have these numbers here is because it comes from the number of elements in a given energy level of each block. Okay, so for example, because the S block only has 1 subshell, but each subshell can hold 2 total electrons, every single energy level in the S block can hold a total of 2 electrons. So what I mean by that is, here's our S block, okay? So if there is an element here and an element here, right? Lithium has an extra electron compared to helium, and beryllium has an extra electron compared to lithium. So if this section right here, these yellow and orange boxes, are our S block, okay, lithium has an extra electron and beryllium has an extra electron. I mean, as we move along in the periodic table, right, from helium to lithium, we gain an extra electron. From lithium to beryllium, we gain an extra electron. Okay, so in this energy level, right, in energy level number 2, in the S block here, we have an extra electron from lithium, an extra electron from beryllium, which is a total of 2 electrons, right? After beryllium, we're moving all the way over here to boron. But now, keep in mind, we've switched to the P block, okay? So if we're only concerned about the S block right now, the 2 electrons that correspond to any energy level represent the fact that there is 1, 2 elements that add in an extra electron every time on any of the energy levels within the S block, okay? So in the energy level 4, in the S block, we have elements potassium and calcium, okay? So as we go from argon to potassium and we gain an extra electron, that electron represents 1 spot in the 4th energy level in the P block, okay? So we would call this section the 4P subshell because it's in the 4th energy level with, or 4S, excuse me, sorry, 4S, because it's in the 4th energy level in the S block on the periodic table, okay? So since we haven't looked at any examples yet, you might be kind of confused in terms of thinking, what are we actually doing with this and how does this help us understand the structure of atoms? And what we're really going to be doing is we're going to look at structures similar to this that represent each of these subshells for all of the blocks for each energy level. And we basically take an atom and we say, okay, if we have a calcium atom, let's figure out, based on the energy differences in these different levels and the subblocks on the periodic table, where are we actually going to find every electron within that atom? So we're going to start drawing lines like this that represent each subshell within the periodic table and fill in where we find those electrons if we have a calcium atom. So if we have a calcium atom and calcium's right here, so it's element number 20, all right, so we know that it's going to have a total of 20 electrons. When you write out the electron configuration for calcium, hopefully you would know that there are 20 electrons here, but you would have to figure out, based on knowing that there are 20 electrons and looking at where it's at in the periodic table, okay, so calcium is the element that ends electrons filling in the 4s2 block, okay, or 4s2 subshell, because it's on the 4th energy level, it's in the S block, and calcium is the second element in the 4s energy level. Okay, so we'll take a look at those examples later, but before we actually start coming up with pictures or diagrams that look like these lines here, we're going to draw arrows that represent the electrons on these different lines. But before we do that, we need to figure out a couple initial rules that tell us how to fill in these electrons and what order we should be filling them in. So let's take a look at some of these rules. Okay, the first one here is called the Offbow Principle. Now, this comes from the term or the phrase Offbow Principle, which is German for the phrase to build, which basically represents here that we're going to be building up this electron configuration to show where all of the electrons occupy different energy levels within an atom of calcium, for example. Okay, now what we're going to be learning here is that in the ground state of an atom or ion, remember the ground state is the lowest energy level, electrons fill atomic orbitals of the lowest available energy levels before occupying higher levels. Now, this is almost always going to be the case when we go through these problems until we come across ions. Okay, now we'll get to that later. But when we're talking about the simpler versions of these problems, it's really just going to say, write out the electron configuration for calcium or for a calcium atom. Okay, so all you have to be able to do is organize these energy levels, okay, based on something like this format. Now, a lot of times we just write it in a straight line, so it'll be 1s and then 2s and then 2p. As you can see, they increase their energy like that. So sometimes we write them out flat, which is how you're going to see me write them later on. But this is a good representation to show you how we go from one to the next, to the next, to the next, based on their energy levels, okay? And this represents how we looked at the, oh, here we go. how we looked at the Bohr models when we were talking about electrons absorbing energy, right? If we have some kind of infrared or electromagnetic radiation, these electrons can jump up in energy levels when they absorb energy, okay? So this is the same kind of concept in terms of the energy distribution between all of these subshells, okay? So again, for almost every single problem, we're going to be filling them in based on the ground state, okay? So assuming we don't have any energized electrons, which makes this really simple. Okay, so just again as a refresher, the ground state is the lowest energy state of a quantum mechanical system, such as an atom, okay? So when the atom has its lowest amount of energy, and right, we talked about how there's a relationship between energy and stability. So when energy is really low, stability is really high, right? As atoms gain more energy, their stability goes down because they're really ready to be active and to do things like form bonds and create molecules, okay? So in other words, all of the energy in the ground state of a given system, meaning the internal energy of that atom, comes from the system itself, meaning, or as opposed to a system in an excited state which has absorbed outside energy. So in this case, we're assuming we do not have an energized atom, which makes filling in these electrons pretty straightforward. Okay, but there are a couple more rules we need to know about. So the next one is called Hund's rule of maximum multiplicity. This rule states that for a given electron configuration, the configuration with the lowest energy or the most stable configuration will have the greatest value of spin multiplicity, which really doesn't mean anything to us because we haven't started filling these in. But this means that if two or more orbitals of equal energy are available, the electrons will occupy them singly before filling them in pairs. Now, this is kind of confusing until we look at an example, but the way that I like to think about this as a concept is just like if you're getting on a bus, okay? So let's say you're getting on a school bus here. Now, if you're the first person to get on this school bus, you're going to sit wherever you want, right? Because none of these seats are taken. So let's say you choose to sit right here, okay? Now, if somebody else, let's say this is person number 2, now this person's getting on the bus. If they're getting on the bus and you're the first person here, it's not very likely that they're going to come and sit next to you, right? They're not going to just pop a squat right here when all of these other spaces are open on the bus, right? This person's going to want to sit by themselves unless they don't have to. So they'll go over here, okay? Now, if the third person hops on the bus, again, the same thing's probably going to happen, right? The third person's not going to want to come sit next to you or this random person if there are a bunch of empty seats still open on the bus, okay? So they'll come down here, and only when all of these seats are at least half filled are people going to start doubling up on the bus, right? Everybody's going to want to sit by themselves unless they can't, right? Unless there's no other option. So by the time we get to 1, 2, 3, 4, 5, 6, 7, 8 people, okay? Now, as soon as we get the 9th person hopping on the bus, only in that situation are there going to be 2 people to a seat, okay? Because everybody else was able to get their own seat first. So now we start having to double up, okay? Now we'll look at what this means in terms of electron configurations when we start doing practice problems, but this is a good way to think about that concept, okay? So we'll take a look at the oxygen atom as an example in just a minute, but let's get through some of these rules before we take a look at some examples. Okay, so the last rule here is called the Pauli exclusion principle. So the Pauli exclusion principle states that 2 electrons cannot occupy the same quantum state or have the same set of quantum numbers at the same time within a given system. So again, the system that we're referring to is a single atom, okay? This means that 2 electrons in the same subshell cannot have the same spin, and we don't know what that means yet, but we'll fill that in just a second. Therefore, if an electron is filling a subshell that already contains an electron, it must have opposite spin, okay? This is important for when we get to examples. So quantum numbers are a set of numbers that can explain any specific electron within a system. Okay, so again, for example, if we're looking at a calcium atom and we know it has 20 electrons in it because its atomic number is 20, when we write that electron configuration, because we're not getting into the specifics of any kind of quantum mechanics, there is a way to determine or label every specific electron within that atom when we write out the electron configuration, okay? So every electron within that atom will have a specific energy level, a specific orbital, a specific subshell, and a specific spin direction, all of which we'll look at in some examples. But again, another good way that I like to think about this is if you're on the bus, you are sitting in a seat, right? So as soon as 8 people fill up these seats and we start having to double up, if this 9th person is hopping on the bus, they're not going to come sit on top of you, right? You are already sitting in that seat. This person cannot occupy that spot because somebody is already there, right? The closest they can get is to sit right next to you, okay? That's their next best option. But they cannot take up a seat that you are already in because you're already sitting there, right? And the same principle applies to electrons. If we're filling different spots to represent where electrons are in an atom, if an electron's already in some spot, it can't be just sharing that spot with another electron, okay? That electron would have to move to the next seat that's open. So again, we'll take a look at this when we get to some examples. So before we move on, let's take a look at what does this actually look like when we try and fill out a problem like this. Okay, so let's do oxygen first. So let's take a look at oxygen on the periodic table. I'm going to go back here so I have this up in front of me. But oxygen, as we can see, is element number 8, okay? Because its atomic number is 8, we know it has 8 protons in the nucleus, which must mean that a stable ground state atom would also have 8 electrons to balance that out, okay? So we have a total of 8 electrons here, which means when we write out our electron configuration, we need to account for where each of these 8 electrons is. Now, the way that I'm going to do that is based on figuring out where is oxygen in the periodic table, okay? Meaning, which block am I in, okay? Which energy level am I in, and how far over am I in that block? So, for example, not this one, oxygen is in the P block, okay? It's over in the right section of the periodic table. Now, in the P block, if we go all the way across to the left, we can see that it's in energy level 2. Okay, so our oxygen is going to be somewhere in the 2P subshell. Okay. Now, within 2P, once we move out of 2s, right, beryllium is the final element in 2s. Okay, if we're looking at our periodic table here, here's 2s, and we jump over to 2P, which starts at element boron, okay? Meaning that in 2P, boron is the first element, meaning boron consists of the first electron in the 2P subshell, which means carbon would be 2P, 2 electrons, nitrogen would be 2, still in the P block, 3 electrons, so oxygen is 2 in the P block with 4 electrons, okay? So we need to end up with a total of 2p4. So the way that we represent this is 2 is the energy level. Okay, P is our block. And 4 is the number of electrons in that subshell. Okay, now we'll see what this looks like when we draw it out. Subshell. There we go. Okay, so like I said, we usually write them out in a straight line, but we write them out the same way that they are ordered here based on their energy levels. Okay, now this follows the trend that we would count through 1, 2, 3, etc., all the way through the periodic table. Okay, so we start with 1s because 1s, up here, 1s is the lowest energy level for those electrons to fill spots in, okay? And then they'll have to fill higher and higher energy level spots as we move on. But like we said in the Offbow principle, right, we have to fill the ground state first. And if the ground state sections are all filled, then we continue to fill the lowest energy level as we move on, okay? So I'm going to write these out all linear, but I'm going to write them out in the same order, okay? So 1s is the first energy level that we have. So I'm just going to write a line here. This represents the 1s subshell block, okay? Energy level 1, block S, subshell 1s, okay? Now, after 1s, what's the next most energetic? 2s, okay? Because after 1s, right, 1s is finished with helium. After that, we move down to 2s, which is element number 3, right? Lithium and then beryllium. So those are the next most energetic locations. Okay, so next is 2s. And again, I only know there's one subshell for both of these because each subshell can hold 2 electrons, okay? So s blocks have one subshell per energy level, all right? But each of these subshells can hold 2 electrons. So we'll see what it looks like in terms of filling those in order once we figure out where our last energy level is, which will be dependent on where the element is in the periodic table that we're talking about. So like I said, we're talking about oxygen here, and oxygen is in the second energy level in the P block. So it's in the 2p subshell, which is actually right here. Okay, the 2p subshell comes after 2s. So I'm going to fill that in. 1, 2, 3. So all three of these sections, all three of these subshells represent the 2p block. Okay, now again, because each subshell, or there are 3 subshells in the P block, each one can hold 2 electrons. That's a total of 6 electrons. Why is it a total of 6? Well, if we look at the periodic table, if this column, or if this row, that I'm highlighting here, around boron to neon, right? Boron, carbon, nitrogen, oxygen, fluorine, neon, all of these elements represent the 2p subshell, okay? Right? Energy level 2, block P, all of these electrons in these atoms right here. So we know it can hold a total of 6 electrons because we have 1, 2, 3, 4, 5, 6 elements here. Okay, so each of these elements represents adding a new electron as we get bigger and bigger. Okay, so what does it look like to actually fill in the electrons for oxygen? Well, we know we have a total of 8, so we need to fill them in these spots based on the rules we just went over, okay? Now, the way that we fill them in is something that's called spin up first, okay? Now, that's only because we talked about the Pauli exclusion principle, okay? Which basically means that you and another person on the bus cannot share a seat, right? Everybody has to have their own seat. Same thing with electrons. But that also means that when electrons are within the same subshell, they can't have the same spin, which doesn't really mean too much to us, but that means that we have to represent the electrons in here differently, okay? So remember that each subshell in the S block can hold 2 total electrons, okay? Each subshell in general can hold 2 electrons. So if this subshell right here can hold 2 electrons, and spin is one of our quantum numbers, which again doesn't really need to mean anything to us. We just need to know that every single electron needs to be able to be isolated based on its characteristics. Okay, so some characteristics are the energy level, the block, or the subshell. Okay, and then the last one is the spin, which basically means if this electron is pointed up right here, so we use just like a one-headed arrow. So instead of having a two-headed arrow, we just use a one-headed arrow. Just because that's the format that we represent electrons in. But because we need to fill the lowest energy levels first, remember 1s is a lower energy level than 2s, so we need to fill all of 1s before we can move on, okay? And because each energy level, or each subshell can hold 2 electrons, we need to fit 2 electrons here. So the way that we would represent the second electron so that it still has the same energy level in the same shell, in the same subshell, but it has to have a different spin, is just that we flip this upside down to represent that it has down spin, okay? Now again, this is more complicated when we get into quantum mechanics, but just know that if we had 2 electrons here, technically those represent the same thing, okay? Even though they're in 2 different spots, right? It's not exactly the same as the bus analogy, but both of these electrons, if you wanted to categorize them, they'd both be in energy level 1, they'd both be in block S, so they'd both be in subshell 1s, and if they both have the same spin, that means that these are the same electron, okay? Or if they're different electrons, they're occupying the same spot, which again, just like on the bus example, you can't have 2 electrons that occupy the same space. So just as a kind of matter of how we use the convention to represent this, the second electron needs to be spinned down to represent that it is in the same subshell So it has the same energy, same block, but it's technically a different electron, right? It's not occupying the same space as this first one. So just by matter of convention, one has to go up and one has to go down within every subshell, okay? So far, we've taken account of 2 electrons. Okay, here are our first 2 electrons, which means we have 6 more, okay? Now, again, because we have to fill them in the ground state and then move up in energy levels as we do, the next energy level that we can fill is 2s, okay? So we can add in electrons for 2s. Again, the first one needs to be spin up because in this case, the 2s subshell represents 1 seat on the bus, or 1 row of seats on the bus. We filled our first spot, but now, because this is a really small bus, the second electron's hopping on and it has to be spin down, okay? Just like in our first example here. We've now filled in 2 more electrons, so we have a total of 4, which means we have 4 more that we need to fill in. Now this is where things get a little bit different, okay? We're in 2p. Notice here how I told you guys that we have a total of 4 electrons in 2p, which should make sense, okay? We've already used 4. We know there's 4 left. And because oxygen is in the 2p subshell, then that's where we are going to finish adding in our electrons, right? We don't really have enough electrons to go beyond 2p, which is probably a good thing because that's not where the atom is that we're talking about, okay? So if we're going to fill in these last 4 electrons, this subshell will make more sense in terms of the bus analogy. Okay, so if we have 4 electrons, we have 1. Keep in mind, the p block can hold a total of 6 electrons, right? 3 subshells. Here's 1, here's 2, here's 3. Okay, and in each of these subshells, right, we can hold a total of 2 electrons. But again, just like on the bus, we have to fill in 1 spot first before we come back and double fill the spot a second time. So here's electron number 1, electron number 2, electron number 3. So now we filled each of these subshells with 1 electron. Now we can come back and add an electron to a spot that's already been half filled because again, just like on the bus, everybody wants their own seat until that's not an option anymore. Okay, which means our 4th electron is going to go right here. But again, it cannot be spin up because we already have a spin up electron here. So it has to be spin down. So now we've accounted for 4 electrons in the 2p block, which means we've accounted for all 8 of our electrons. So in terms of looking at this like an actual problem, oh, I didn't mean to erase that line there. In terms of looking at this like an actual problem, if I asked you to give me the electron configuration for an oxygen atom in the ground state, this right here is exactly what I would expect you to give me. Okay? So just as another example, let's go through one for calcium. Okay? So calcium on the periodic table has 20 electrons because it's element number 20. So we know we should have a total of 20 electrons, all right? And if you're taking account of where it is, it's in the 4th energy level in the S block, and it's the 2nd element in that subshell, okay? Because potassium would be the 1st element in that subshell. So we know that calcium is going to end at 4s2 when we fill in all the electrons, okay? 4s2. All right. So again, we're going to be filling it in the same way we did last time. 1s, then 2s, then 2p, then 3s, then 3p, then 4s, right? Because if we're ending at 4s2, we want to fill them in at the lowest energy level and move up slowly. And because each subshell can hold 2 electrons, okay, just like we had right here, we can have a total of, if we end at 4s and we fill that in, we have 1 subshell here, 1 subshell here, 3 here, 1 here, 3 here, and 1 for 4s. Okay, so if you just count up how many electrons can we fit there, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we end up filling all of the 4s block or subshell, okay? So in order, just like we would have it on the periodic table, we have 1s, 2s, 3 subshells for 2p, 3s, 3 subshells for 3p, and then 1 for 4s at the end, okay? So if we have 20 electrons, what does it look like to fill them in? Well, we have to fill in the first one, okay? Obviously, there's no other seats for these electrons to fill in, so we've got to come back and fill in the second one. 2s, 1, 2, 2p, 1, 2, 3, 4, 5, 6. Notice how I filled in 1 for each subshell first, and then I came back and double filled them all, okay? So far we have a total of 2, 4, 6, 8, 10 electrons, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, okay? So again, if I asked you for the electron configuration for calcium, this is what I would expect as an answer, okay? So this represents where the electrons are all located, or which energy locations, which energy spots are all being filled by the electrons in this atom, okay? Now, if I didn't ask you for the actual diagram, sometimes you'll have to draw it out like this, sometimes you won't, okay? And what I mean by sometimes you won't is you can just write out all of this in order. So for example, since we know that calcium ends its electron configuration at 4s2, sometimes you guys can just write it out as is, meaning 1s2, okay? So this right here represents that in 1s, we have 2 electrons, okay? Now after that, we would write 2s2. Again, 2s2 here represents that in the 2s subshell, we have 2 electrons, okay? After that, we fill 2p, but as you guys can see here, we have a total of 6 electrons in the 2p subshells, okay? So 2p6. So the numbers in the superscripts represent how many electrons do we have in each of those spots, okay? After 2p, we have 3s. So here's 3s. And as you guys can see, we have a total of 2 electrons in the 3s subshell. So here's our 3s2. Again, after 3s, just like with 2s, we have 3p. As you guys can see, in 3p, we had to fill in all 6 electrons for all the subshells. And then after 3p, we have 4s. And in 4s, we have a total of 2 electrons, okay? So this would also be an accurate answer for the electron configuration for calcium, okay? So one last thing I want to mention before we go through a bunch of practice problems and we start talking about this in class is that there are some exceptions to the Offbow principle, okay? The Offbow principle says that we fill based on the ground state and then we go after that, which makes it really simple. However, based on observational or experimental observations, we find that this is not always the case. Now, it's not going to happen very frequently. However, the explanation for this is because, like we've mentioned before, there's a relationship between energy and stability in atoms. So there is a trade-off between energy and balance when more complex atoms can evenly distribute all of their electrons, even if it is not the lowest possible ground state. Okay, so let's take a look at what this really means. So if you were to write out the electron configuration for chromium on the periodic table, we would find chromium right here, okay? Meaning that it is in the 4, but if you're looking at where it is, it's actually in the D block. So it has electrons in the 4s subshell. However, the way that we categorize it, again, based on the energy distribution, 3D actually comes first. So just in terms of how we annotate that, the first energy level in the D block is energy level 3, okay? Now, I know that's kind of confusing, but again, those numbers come from the quantum mechanic calculation. So we don't really need to know why there's a number 3 here, but the easiest way to remember it is that because S is the first block and P is the second block and D is like the third block that we come to, we start block S with energy level 1, we start block P with energy level 2, we start block D with energy level 3, and we start block F with energy level 4. Okay, and that's exactly what we'll see if we look at this block layout right here, right? We start with 1s, P's start with energy level 2, D's start with energy level 3, and F start with energy level 4. So that's just a way of annotating it that you guys are going to have to remember, okay? Now, as you guys might be able to notice, and I think I have that more clearly written down here, as we get higher up in energy levels, the difference in energy between one level and the next gets really, really small, okay? So between 1s and 2s, there's kind of quite a bit of space here. But as we move up, like between 5f and 6d, the energy levels here are really close together, right? You guys can see there's not a huge difference in energy here, which means that it's a lot easier for the atoms to trade off where the electrons are, which spaces the electrons are going to occupy, depending on how we can most evenly distribute the electrons, okay? So when we have smaller atoms and we're dealing with fewer electrons, we're more concerned with the energy distribution, okay? We're not going to have the first two electrons in an atom in the 2s subshell because there's a huge energy difference that they would have to overcome to skip the 1s subshell, okay? But as we get further and further out and atoms get more and more complicated, these energy levels get closer together. So again, for chromium right here, we would expect there to be 1, 2, 3, 4 electrons in the 3d subshell, right? Because the chromium atom is in the D block in the third energy level, and there are a total of 1, 2, 3, 4 electrons here. However, because the D block has 5 subshells, what ends up happening is instead of what you guys would expect, right? We'd have a 4s and then a 3d4. So here's 1, 2, 3, 4, 5 subshells in the 3d block, okay? If we filled in the 4s, because we would expect the 4s to be down here, right? It's at a lower energy level than 3d, we would fill this in first, right? According to all of these principles and rules we just learned. However, from what we find in experimental observations, this is not actually where we find the electrons, okay? We find that one of the electrons from the 4s block is actually what's called promoted or slightly energized to fill in this last subshell here. So now if we have one electron that's spin up in every single one of these subshells, it adds an extra kind of level of stability to that atom because all of these electrons here are evenly distributed, okay? Even though we had to basically promote one of these electrons here to a higher energy state, some of that energy is utilized to add that stability to the atom because now we have an even distribution of these electrons. But keep in mind, you're really only ever going to find this with atoms like these, okay? So for these 4 atoms here, we find that the experimental distribution of the electrons does not match what we would expect in terms of how we would fill it in based on the ground state. But keep in mind, the only examples here all take one of the electrons from the s block, okay? So this second electron here, or if it's in the 5s or 6s, it takes one of these electrons to balance out everything in the D block here, either by having one electron spin up in every single subshell, or for things like copper, silver, and gold, you'll see that the 3D has 10 electrons, 4D has 10 electrons, and 5D has 10 electrons, meaning that all of these subshells are going to end up having an electron spin up and an electron spin down. And again, this just has to do with how we can balance out some of the stability in the atom based on the even distribution of which locations the electrons are occupying, okay? But this isn't going to, we're not going to see this a lot. This is an exception to all of these rules that we've talked about. But we will talk about these and certain examples where we should be thinking about this concept as we continue through class and going over practice problems for electron configurations. So I'll provide you guys some homework for that on our Google Classroom this week, and I will also give you a solutions manual to that so that we can start going through some of them in class and answering any questions you guys have. But like always, take some time to fill out these notes, pause it at any point. And as always, make sure you guys hit that like and subscribe button, and I will see you in class.